Hello and welcome. Yesterday we have studied too many new things. So before proceeding further, we should revise the important concepts that we should remember. We have learned about a new operation called convolution between two signals. Call it x of t and y of t. If these are two signals, then the convolution between them, we write it as x star y, is given as integration of x tau y t minus tau d tau from minus infinity to plus infinity, which is also same as, you can swap the role of x and y. You can write y of tau and x of t minus tau d tau from minus infinity to plus infinity. Next, the very important fact is that for an LTI system, if h of t denotes the impulse response, that means the output when the input is an impulse function. And if this is known, then for any input xt, output will be given by the convolution between xt and h of t, which you can write as the integration of x of tau h t minus tau d tau from minus tau equal to minus infinity to infinity, or the other way, h of tau first and then x of t minus tau d tau from tau equal to minus infinity to plus infinity. Now, what is the fundamental idea behind this complicated formula? That is what we saw, that given any arbitrary input, you can always break it into smaller slices, and when the width of these slices delta t tends to 0, then it becomes a combination, a sum of delta functions, time shifted delta functions. And if you calculate the sum of the response due to individual delta functions, then you get the total output. I think an analogy might help you in understanding and remembering this idea. Consider this water tap. Water falls from this tap and falls on this basin, and it makes some sound. With my hand, I can control the amount of water flow or flow rate. Call that as the input. And the sound that is produced is the output. The loudness or the intensity of sound is the output. Let us hear this. So when water falls, output sound is produced. Now if I control the amount of flow, then the loudness of sound will also change. Listen. Okay. Now listen what happens if I reduce the flow rate to a very small amount slowly. Flow rate is being reduced and the intensity of sound, that is also reduced. Now I shall reduce it further. Now water is falling drop by drop. Each drop you consider as a impulse input to this system, and the resulting sound, tap tap tap, those are impulse responses corresponding to these droplets. Listen. Now I can increase the flow rate gradually. So finally I have a continuous flow of water or continuous input, and the sound produced is also continuous. But this continuous flow is made up of small droplets, or the input is made up of a sum of impulse inputs, and the output sound is also a result of sum of those tap 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 tap, all of them being so continuous that you get a smooth sound. This analogy should help you in understanding the idea of breaking an input into a sum of impulses and then add the output, add the impulse response corresponding to individual impulses to get the total output. So our policy is to divide the input and conquer and get the final output. Next, we have learned very important properties of convolution. If I have two signals Z1 and Z2, then Z1 star Z2 is same as Z2 star Z1. You can swap the order. Next, if you have three signals Z1, Z2 and Z3, then whether you first convolve 1 and 2 and then 3, or you do it other way, 2 and 3 first and then 1, that doesn't matter, it is same. Next, if you have Z2 plus Z3, the sum of two signals convolved with the third one, that is very similar to the rule of multiplication. You can write Z1 star Z2 plus Z1 star Z3 like this. Let us now see some implications of these properties. First, assume that I have two systems, system 1 and system 2. Suppose the impulse response of first system is H1t. This is given. And let me denote the impulse response of the second system as H2t. Now I shall connect these two systems in a particular way. See this. These two inputs I am going to connect together. Therefore, the same input X will go to both the systems and they will produce two outputs, call it Y1 and Y2. Then I shall take the sum of these two outputs somehow I will add these two, and then this will be my final output, which is the sum of Y1 plus Y2. For an example, you can think of two generators and the input is the speed at which they rotate. You have connected the axis, the shaft of the two generators so that they rotate at the same speed. So same input is going to both the systems, and consider output as the generated voltage. Then you can add the two voltages by connecting them in series. This way you can connect two systems like this. This is called parallel connection. Okay, so this way you can connect two generators in parallel like this. Now what will be the final output? Let's calculate. Y1 I can write as X star H1, convolution between input and impulse response. Similarly, Y2 will be X star H2. Therefore, the final output will be X star H1 plus X star H2. Now you can take X common, H1 plus H2 star here. So this will be the final, this is H2, X star H1 plus H2. This is the final output. Now suppose you want to replace these two systems together by one single system. Suppose you want to replace these two generators by one single generator or single system. Whose impulse response is Ht, and you want to do it in such a way so that when you replace these two systems by one system, and if you give same input xt, then you should get same output yt as before, as the effect of two systems. Then the question is, what should be the impulse response of this system? I can write here that output will be X star H, and if I want these two outputs to be same for same input X, that means these two are same, then I can write that H should be equal to H1 plus H2. Consider another situation. Again, I have two systems. System 1, whose impulse response is H1t, and system 2, with impulse response h2t. Now I shall connect these two systems in a particular way. Suppose the input to the first system is xt. That will produce our output yt, and that output I will feed as the input to the next system. It will now produce our output y2t, and that will be my final output yt. Now this is called cascade connection. Now how will this output look like? So for that, let me first write y1 as x star h1, and then y2 is same as x2 or y1 star h2. So this is equal to x star h1, that is the input here, star h2. So this can also be written as x star h1 star h2, but bracket here. This is true by virtue of the associative property. Now then I can write it as x star h2 star h1 because of the commutative property, and then again using associative property I can write it as x h2 whole star h1. Now what does this mean? This means if I connect a system with impulse response h2 followed by another system whose impulse response is h1t, and these two are connected in cascade, so that the input comes here xt and the final output is here. Then this output will be same as this output, because in this case you can calculate here the output will be x star h2, and then take this x star h2, convert this with h1, that is the final output, which is same as this. So it means that you can reorder these two systems. You can swap the order of these two systems. If the input outputs are compatible, you can swap the order and the input output behavior remains unaltered, unchanged. Now a very nice implication of this equivalence we shall see now. Suppose we want to find the impulse response of a given system, we want to do it experimentally. So if this is the system given to us and we want to find the impulse response, call it HT, we will have to do an experiment. We will give input xt equal to delta t, and then we shall measure the output. Measure this output or observe this output. This will be same as h of t by definition. If you give delta t as the input, by definition output is the impulse response. However, there is a problem. The problem is that in laboratory you cannot get ideal impulse signal, because this is ideally very narrow, very tall, infinitely narrow. That idealistic situation is not possible. We can get some approximation. We can work with a very tall but very narrow signal. But there is another way out, another solution. That is like this. Consider a system which works in the following way. It takes a signal xt and produces output which is same as the derivative of the input. So this you can call a differentiator, ddt. So this is the operation that this system does on the input signal. Okay, now what I shall do, I shall take the unknown or given system, given or unknown system whose impulse response ht is unknown to me, and that is what I want to find out. Then suppose in theory I connect this differentiator in cascade like this. Imagine this we do in theory, such that some input x comes here, then the derivative goes to the input of the unknown system and output is produced. Now if I take xt equal to ut, you remember what is ut? Ut is step signal like this, 0, 1 at t equal to 0. Then what do we have here in theory? In theory here we shall have ddt of ut which is same as delta t. Derivative of step function is impulse function, unit impulse function. Therefore what shall we get here? H of t. So in theory, if we imagine to connect a differentiator before this unknown system, and here if we give the input which is unit step function, and then if we measure the output, then that will be the unknown impulse response. Now in theory we have already learned that we can swap the order of these two systems. So now you imagine that we have the given system first here, and then it is connected to the differentiator. Then if I give the same input here, xt equal to ut, then what will I get here? I will get the same output as here, which will be ht. So I can do this experiment in theory as well. Take the unknown system, then after that connect the differentiator in Cascade. Here you give unit step function and measure the output. Whatever you measure, that will be the impulse response of the unknown system. And in laboratory, it is easier to get step function because there is no business of infinity. You can produce step function, more realistic step function easily. So if you give step function here and suppose you measure this output, measure this and call it say GT. I can give this GT a name. I will call it step response, because this is the response or output of the system when input is a step function. So call it step response or GT. This you can measure, and then on pen and paper, even on pen and paper, you can perform the differentiation on the step response. The result will be impulse response. So the conclusion is this: since it is difficult to get impulse function in laboratory, you can do the following experiment. You give step function as the input, give ut as input. This is step 1. Then step 2, measure the output of the system, that you call GT. And then step 3, calculate ddt of GT on pen and paper. Okay, that will give you the impulse response. This way in laboratory you can calculate impulse response without requiring a impulse function as the input. Derivative of step response is the impulse response. According to our divide and conquer policy, we have learned that any input can be broken as a sum, infinite sum of impulse signals. And if you know the impulse response, then from that you can calculate output for any arbitrary input pattern. So for an LTI system, all that we need to know is the impulse response. If we know impulse response, we know everything about the system. So some obvious questions arises that can we then tell whether the system is stable or not, causal or not, etc. from the impulse response? Because impulse response carries all the information that one may ask for. So can we say whether the system is causal, memoryless or stable from impulse response? That is what we shall see now. Causality determining causality from impulse response. H of t. It is very simple. Note that output yt is given as integration of x of tau h t minus tau d tau, tau running from minus infinity to plus infinity. Now to calculate the output, say at any particular time, for example at t equal to 10 seconds, this is given as x tau h t minus, here I have to write 10 minus tau d tau, and tau running from minus infinity to plus infinity. This you can then write as two integrations, x tau h 10 minus tau d tau, tau running from minus infinity to up to 10 plus 10 to plus infinity x tau h 10 minus tau d tau. Now here the integration is over minus infinity to tau, minus infinity to 10. So the values of x 10, 9, 8, 7, 6, 5, those values will be required to calculate this integration. That means you need to calculate this integration, you need values of input x at 10, 9, etc. 10, 9.5, 9.1, everything. But you do not need value of x after t equal to 10. But to calculate this part of the integration, you need values like x 10.1, x 11, everything, because it starts from 10 and goes up to infinity. Therefore, this part depends on future input after time t. We are calculating output for time 10, but it requires input after time 10. Okay, so this part can make the system non-causal. However, if say h of 10 minus tau is 0, let me write here, if h of 10 minus tau is 0 for tau greater than 10, okay, this integration runs for tau greater than 10. But if this part is 0 for tau greater than 10, then I don't have to calculate this integration. Then I do not need to know the value of input at times after 10. Okay, then output does not depend on future input, which means the system will be causal. Okay, so the condition I will write here, as you saw that h 10 minus tau should be 0 for tau greater than 10, which is same as writing that h tau equal to 0 for tau less than 0. Here if tau greater than 10, that means these become negative. So that is what I write here, that if the argument is negative, then the value is 0. If that is the condition, if that is the situation, that means the system is causal. Next, let us talk about determining memoryless or memory with memory or without memory system, determining presence of memory. From impulse response ht. Once again we will use the same trick. We will write yt as x tau h t minus tau d tau from minus infinity to infinity integrated, and then note that to calculate the output at any particular time like y10, you can do this integration x tau h 10 minus tau d tau from tau equal to minus infinity to plus infinity. Then you write it as a sum of 3 integrations like this: 1, 3 integrations. I will just copy. Okay, so one of them from the range minus infinity to a point slightly before 10, 10 minus slightly before 10, plus integrate within the range from 10 minus to 10 plus. So this is around near the time t equal to 10 plus the remaining part from 10 plus to infinity. Now observe that to calculate this part we need only x10. However, to calculate this part of the integration here we need x tau input for tau less than 10, and for this part we need input x tau for tau greater than 10, but we are calculating output at time 10. So if the system is memoryless, then the output should depend only on the present input. It should depend only on x10. Therefore, for a memoryless system, only this part of the integration should survive and these two somehow should be 0. So for a memoryless system, this part of the integration should be 0 for memoryless system, and this part should also be 0 for memoryless system. Only this part should survive. Now how could that happen? That could happen only if say ht is equal to 0 for t not equal to 0. If say that is the condition, if ht is 0 whenever the argument inside is non-zero, that means in this integration tau is less than 10, so inside bracket we will have some non-zero number, some positive number, and therefore this will be 0. So this integration will result into 0. Similarly, here the range of integration is greater than 10 to infinity. So inside the bracket we will have some number which is negative, non-zero. Therefore this integration will also result in 0 if ht is 0 for non-zero time value. So this is the condition for memorylessness. So this is the condition for memorylessness. That means for a memoryless system, impulse response ht will be a impulse function because it is 0 everywhere other than at t equal to 0, but it can also have some constant multiplied that will not affect the memorylessness. So this is the condition. For a memoryless system, the impulse response is an impulse function multiplied by some constant. Now we shall talk about determining stability from impulse response ht, and particularly we shall talk about Bibo stability. Please recall what we mean by Bibo stability. For Bibo stable system, if the input is bounded, that means the mod value, absolute value of xt is less than some number, call it m1, for some m1, then output is also bounded and it is less than some m2 for some m2. Now let me first write the condition, then I will justify. So the condition is, if ht, take absolute value of that and then integrate that over entire period of time minus infinity to plus infinity, if this is say less than some number, call it m, that means this is finite. Then the system is stable. That means this infinite integration, if it results into a finite number, then the system is stable, or else the system is unstable. Let me prove it. Okay, so suppose it is true that the integration of mod ht over time t equal to minus infinity to infinity is suppose less than a number m. Then the output y of t at any time can be written as the convolution of xt and h t minus tau d tau, tau running from minus infinity to plus infinity. This you may also write in this way: x t minus tau h tau d tau, because of the commutative property. And if the input is bounded, that means x of t for all values of time is less than some number m1 for all time. Okay, then then I can write that the modulus of yt will be same as the modulus of this or this, and that can be written as less than or equal to the integration of the modulus xt minus tau h tau d tau minus infinity to plus infinity. Right. Okay, so the modulus of sum is less than or equal to the sum of modulus. Now this is equal to xt minus tau mod of that and h tau mod of that. Modulus of the product is same as the product of the modulus, d tau minus infinity to plus infinity. Now we know that the value of x is always less than m1. Therefore I can write this as less than m1 h tau d tau from minus infinity to plus infinity. This value is always less than m1, so you can take it outside and write it as less than this term. Okay, and now by virtue of this fact here, that this integration is less than m, it is finite, I can write this is less than equal to m1 and this is m multiplied by m. Now we can call it m2 So this implies that output, mod value of output, is always less than a number m2. So we started from the assumption that this integration is finite and have proved that this system is stable because output is always bounded. Now let me prove it the other way. So suppose this integration of modulus of ht dt from minus infinity to infinity is not finite, or it does not converge. Then I shall prove that this system is unstable. For that, let me first write yt equal to integration of x tau h t minus tau d tau from minus infinity to plus infinity, and let us consider output at one particular time t equal to 0. That will be same as x tau h 0 minus tau, which is same as minus tau d tau from minus infinity to plus infinity. Now I will choose the input in a way to make this output infinite. So I will carefully choose the input. Suppose I choose input xt such that xt is equal to sine of h minus tau, h minus t. What does this mean? It means xt is equal to plus 1 or minus 1 depending on whether h minus t is greater than 0 or h minus t is less than 0. So this gives the plus minus sign of ht. Now if I choose in this way, then this output can be written as, in place of x I write sine of h minus tau, then this is as it is d tau minus infinity to plus infinity. Then you notice that this is same as the modulus of h of minus tau, because if h minus tau is positive, then this is just plus 1, it does nothing. But if this term is negative, then this is minus 1, so it makes it positive. Therefore I write it as the integration of modulus of h minus tau d tau, and then with a change of variable you can replace minus tau with t, and then it will become h t dt integrated from minus infinity to plus infinity with a change of variable. However, this quantity, as we have assumed, is infinite. This implies that y0 is not finite, not bounded. So output is not bounded at least at one point of time. By choosing this particular input, we can make the output unbounded, but here the input is bounded. It is either +1 or -1. It is never infinite. So we can choose an input which is bounded, but that makes the output unbounded. So it implies the system is unstable. That means if this integration is not finite, the system is unstable, and previously we have shown that if this integration is finite, then the system is stable. Before proceeding further, I will just remind a very important thing, that is the formula yt equal to x tau h t minus tau d tau from -infinity to +infinity. In short, x convolved with h is valid. This formula is valid for only LTI systems. If the system is not LTI, then impulse response is not useful, because you cannot write output in this way. And therefore the conclusions that we have drawn previously about the stability, about the causality, etc., memorylessness, these conditions that we have written, it is true only and only for LTI systems. If the system is not LTI, then these proofs are not valid, because we cannot write this. Yet for those systems you can determine whether they are causal, memoryless or stable in other way, from the input output relationship maybe, but you cannot use this formula, this criteria, that this is the criteria for memorylessness, or this is the criteria for stability, or this is the criteria for causality. These are true only for LTI systems. For other systems, these are not true. Since we have some time left, it will be a good idea to summarize all that we have learned now. Okay, so first of all, we have learned the convolution operation between two signals called xt and yt. This is given as x tau h t minus tau d tau from -infinity to +infinity, which is also equal to x t minus tau and h tau d tau from -infinity to +infinity. Then the properties that we have learned about the convolution is that x star y is same as y star x star y star z is same as x star y whole star z. Next, x of x star y plus z is same as x star y plus y star z. Next, impulse response. This is nothing but the output corresponding to the input x t equal to delta t. To be more precise, under initially relaxed condition. Under initially relaxed condition, if you give delta t as the input, you shall get ht impulse response as the output. However, we have also learned that in laboratory you cannot get delta t, so ht can be found by calculating time derivative of step response of a LTI system. This may not be true in general, but it is true for LTI systems. Next, for LTI systems, from the impulse response, you can say whether it is causal or memoryless or stable, etc. Like this. If h of t is equal to 0 for t less than 0, then the system is causal. Actually, you can remember this in the following way. Suppose if you are giving input which is a delta function at t equal to 0 to the initially relaxed LTI system, this is delta t which goes as the input, and what comes out is ht. Now suppose ht looks like this. So it is non-zero before time 0. Can the system be causal? No, because input is given at t equal to 0, but its effect is seen earlier. So it is obvious if ht is non-zero before t equal to 0, the system is non-causal because the effect or output is coming before the cause or the input. So this is non-causal. And if I have impulse response which is like this, this is 0 before time 0 when the input is given, then this is causal. So there is no effect before the cause. Next, B. If ht is k times delta t, then the system is memoryless. Again, this is easy to remember and understand. Assume The same thing, let me copy. We are giving delta t as the input, and if this impulse response looks something like this, then the effect of this input is seen even after the input is gone. Here the input is gone, the input is 0, but its effect still persists. So the system remembers what happened earlier. So this is with memory system. However, if the output is also impulsive, that means output exists only at the time when the input is given, then this is without memory. Because the system does not remember what happened earlier, or it does not know what is going to happen in future. So it reacts immediately to the input, and when the input is gone, output is also gone. So this is the condition for the system being memoryless. Last, C. If the integration of the modulus of impulse response is finite, that implies stable system. And if it is not finite, then unstable system. And these properties are true only for LTI systems. Okay, thanks a lot. Goodbye, and come back tomorrow to have another nice day.